Problem 6.55 or 7.53 for the given textbooks. For details, please see the description below. A refrigerant R134A enters the condenser of a residential heat pump at a pressure of 800 kilopascals and a temperature of 35 Celsius with a rate of 0.018 kilograms per second and leaves at 800 kilopascals as a saturated liquid. If the compressor consumes 1.2 kilowatts of power, we need to determine the coefficient of performance of the heat pump as well as the rate of heat absorption from the outside air. The first part that we need to evaluate in this heat pump is what happens in the condenser. So where we could find out what is the amount of heat rate that is being rejected. In order to do that, we need to find the conditions that we had at the inlet and at the outlet of the condenser. We need to find the values of enthalpy at both points. Let's just start with the inlet. We know that the pressure is equal to 800 kilopascals and the temperature is equal to 35 Celsius. We go to table 812 in order to find out what is the phase of this particular refrigerant. Notice that at 800 kilopascals, the saturated temperature is equal to 31. Therefore, according to the temperature that we currently have, which is 35 Celsius, we could determine that the refrigerant at the entrance is a superheated vapor. Now that we know that it's a superheated vapor, we go to table 813. We go to the section where we have a pressure of 800 kilopascals and we have a saturated temperature of 31.31 Celsius, just at this point. Our given temperature is 35 Celsius, so we have to interpolate between the saturated temperature and 40 Celsius. And the values that we're going to have are going to be 267.34 and 276.46. By using the values that are provided in the table, we could find out that the enthalpy for 35 Celsius is going to be equal to 271.24 kilojoules per kilogram. Now let's find the value of the enthalpy at the exit. Once again, we go back to the table or a pressure of 800 kilopascals, and notice that is a saturated liquid. So we go across to the value that we have over here and we get that it's going to be 95.48 kilojoules per kilogram. In order to find out the amount of heat rate rejected by the condenser, we're going to do a balance of energy. We have the heat rate going into the condenser plus the power going in plus the energies that are being carried by the fluid, and that is the summation of the enthalpy, the kinetic energy, and the potential energy. That has to be equal to the heat rate that is lost, the power leaving, and the energy being carried by the fluid. Once again, enthalpy, kinetic energy, and potential energy. Assuming that the piping going in and out of the condenser are the same, indicates that the value of the velocities remain the same, having the same cross-sectional area. We could assume that the potential energy remains constant. If the elevation of the entrance and the exit of the condensers are neglected, that means that the potential energy could also be neglected. The condenser doesn't have any power going in or out or produced or needed, and there is no rate of heat going into the condenser. The only value that we have is the heat rate rejected by the condenser. And that's what we're looking for. Q out, which is Q dot high, is equal to the mass flow rate. And then we have the difference between the enthalpy at the entrance and at the exit. We evaluate the mass flow rate. It's a value of 0.018 kilograms per second. And the difference between the enthalpies, we have 271.24 kilojoules kilograms minus 95.48 kilojoules kilograms. Notice that this value is going to give us 3.164. The units, we have kilograms and kilograms cancel, and we have kilojoules and kilojoules divided by second, and that gives us kilowatts. Now that we have the rate of heat rejected by the condenser, we could find what the coefficient of performance of the entire heat pump by using the value of the power entered into the compressor and the heat rejected by the condenser. So the coefficient of performance for this heat pump is going to be equal to the amount of heat, that amount of rate heat that it was rejected, divided by the power going into the compressor. That gives us 3.164 kilowatts divided by the power, which was equal to 1.4 kilowatts. That means that the coefficient of performance of this heat pump is equal to 2.64. The last step is to find out what is the rate of heat absorbed from the outside air. This is done by the evaporator. If you think about it, the amount of power going into the compressor is the difference between the amount of heat that it was rejected and the heat that it was absorbed by the evaporator. So we have that the power going into the compressor is the difference between the rate of heat rejected by the condenser and the rate of heat absorbed by the evaporator. So if we solve this equation for Q dot L, we find that is going to be simply QH minus the power going into the condenser. And the values that we had previously were 1.164 and 1.2. Both of them are in kilowatts. Therefore, the difference is 1.96 kilowatt, and that is the amount of rate of heat absorbed by the evaporator. Couple of notes about this problem. The values for the rate of heat absorption by the evaporator or the rate of heat rejected by the condenser, none of those values could be negative. They always have to be positive. In addition, the amount of rate of heat absorbed by the evaporator always has to be less than the amount of rate of heat rejected by the condenser. The last one is that the rate of heat absorbed by the evaporator can never be zero.